Hello and welcome to this lecture. So, as we start our study of limits and derivatives, particularly limits before we go into derivatives, the most important starting point is sequences of real numbers. Okay, supposing I give you a sequence of real numbers, a large, an infinite sequence of real numbers, on and on and on. If it keeps on coming, what is going to happen eventually? Okay. So, this is something that is at the heart of taking limits, at the heart of understanding functions, heart of continuity, everything. Okay. So, it is very important to understand what happens to sequences of real numbers, and we will study them next. Okay. So, here is a definition. Let's begin with the definition. This is sort of a formal definition. The first time we are seeing a formal definition in this class. Here is a definition. A sequence of real numbers is a function from the set of non-negative integers. I am using non-negative integers here. You can also use, you can throw away 0 and use positive integers if you like. That is not a critical part of the definition. It is a function from the set of integers to the real line R. Okay, so from this to real line. What does it mean? Once again, you know what a function is, right? Function, for every input, you have to specify a unique output. That's function, right? So, what is my input? My input is coming from the domain. I have said it is the set of non-negative integers just for concreteness. You can say set of positive integers, set of any integers, it is okay, it does not matter. Okay, so you have a domain here which is the set of integers and the range is the real numbers. Okay, so for every integer, you have to assign a real number. Now, why is this a sequence? You can see when you assign, like for instance, here is a notation. Let's look at this table. This is very interesting to see why these things are called sequences. So, these functions are denoted a sub n. Okay, so a sub n. Why n? Because usually integers are denoted with this n type thing. And you notice here n takes value 0, 1, 2, etc. And this a n, which is the value of the function for n equals 0, it becomes a0, a1, a2, etc. So, you see it comes in sequence, right? This function which is like a0, a1, a2, a3, so on, it is actually a sequence. So, we call it conveniently as a sequence. Okay, so you should notice how sequence is some English word that you know already. Sequence is something one comes after the other, right? How we have mathematically precisely defined it as a function. Okay, so this level of precision is what makes math sort of a little bit scary. Some people look at this definition and say, I know what a sequence is, why are you defining all these things? But that's important also, right? So, you should know how the definition converts into how you actually use it. So, all you're doing is this, right? So, you have a sequence an, but watch for all this notation. Okay, so this notation is important. N is a notation we often use for integers. An is the value of the sequence at n, right? So, value 0, a0, I mean n0, a0 is the value of the sequence, n is 1, a1 is the value of the sequence. So, notice how I say a0, a1 for this, but I write it subscript, right? The 0 is a subscript, a subscript 0, a subscript 1. Usually people say just a0, a1, a2 for these things. And the sequence itself is denoted using this curly braces an. Okay, so I put an here, and if I put these curly braces around it, it is something that denotes the entire sequence. While an denotes only one value that the sequence takes at n, this curly braces denotes the entire sequence. Okay, so I've shown you a bunch of examples here. We will see a lot more examples as we go along. The first example is very simple, an equals n, sort of like the integer sequence itself, right? 0, 1, 2, 3, the sequence is the entire thing. Another example here, notice I'm slightly complicating the definition. I'm saying it's minus 1 whole raised to the power n. So, if I put n equals 0, I'm going to get 1, n equals 1, I'll get minus 1, n equals 2, I'm going to get 1 again, n equals 3, I will get minus 1. So, notice this is like an alternating 1 minus 1, 1 minus 1, sort of periodic repetition of 1 minus 1. Okay, so that is that sequence. Here is yet another sequence that often comes. I have written it as 1 by n plus 1. The reason why this n plus 1 comes is, I would ideally like to have 1 by n, right? Because that's the sequence, right? 1 by 2, 1 by 3, 1 by 4. But unfortunately, I'm starting at 0 instead of starting at 1. So, I need to have 1 by n plus 1 to make sure that I don't have like 0 in the denominator. Okay, so that's why it is there. Later on, we will start at 1 instead of 0. At that time, it will just be 1 by n. So, this 1 by n sequence, it's very, very important. 1, 1 by 2, 1 by 3, 1 by 4, so on. So you can see that this has a different nature, right? So 1, 0.5, 0.333, 0.25, so on. So notice different types of sequences can be generated, and you can come up with any sequence you want, right? I've put some formula here, it doesn't matter. You can just say 0, 10, 15, 12, 3, 4. You can just, it need not be even in increasing order, right? You can go back and forth. You can go like 100 after 100, you can go to minus 10, 11. There is nothing that stops you from defining a sequence any which way you want, okay? So anything that you can define as a function is a sequence, okay? So sequence is really generic. What else can we do? What are the other types of sequences? Very interesting sequences that occur in practice usually are defined by recursions. Okay, so this is now we are getting slowly into the meat of things. So if you just define sequence any which way you want all over the place, there's no point in studying it. It may not even occur physically or in reality or in science or engineering. Most sequences that occur and are important to study are usually defined by recursions. What do I mean by recursion? Let me give you this very famous example for recursion, which is this Fibonacci sequence. What is this Fibonacci sequence? It starts in a very humble way, A0 equals 0. Okay, that's how it starts. And then A1 is 1. Okay, seems simple enough. A0 is 0, A1 is 1. And then there is the recursion. Okay, notice this recursion here, it's a beautiful and simple thing. It says here an plus 1, the subscript entirely is n plus 1. The next one after an is actually going to be the sum of an and an minus 1. So an plus 1 is an plus an minus 1. And this is for n greater than or equal to 1. Okay, no, I think, yeah, 1 is also okay. Okay, so if I put n equals 1, what happens here? It gives A2 is A1 plus A0. Okay, do you see that? A2 is A1 plus A0. So that's what it means. It's easy to see that. A2 is A1 plus A0. A3 is A2 plus A1, so on, right? So that's the general definition of this recursive equation. So I know how to produce this sequence now. I start with 0. The next one is 1. What is the next guy? Is the sum of these two fellows. That's 1. What about this guy? Sum of these two. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 13 plus 8 is 21. 21 plus 13, 34. So on, so on, so on, so on, so on. You can keep on going. So notice how with this one recursion in a very convenient short way, I have represented or I have specified the entire sequence. Okay, that's why these recursions become powerful. You have a very simple small equation and somehow it captures this complicated behavior with some infinite number of things going on. Okay, so over and over and over again. So that's why recursions are very useful in practice, and this is something that's useful also. We'll come back and see it later, but this Fibonacci sequence is very famous. I just wanted to point out it is a sequence defined by a recursion. There are also other famous sequences you might have studied. You might have studied about arithmetic progression. A lot of things in life happen by arithmetic progression, as in this is the way in which the arithmetic progression is defined. It's again a recursive definition. How does that work? There is one d which is called the common difference in arithmetic progression, and the n plus 1th value in the sequence is the nth value plus this d. Okay, very simple. So you have the nth value, you add a d, you get the n plus 1th. Then you add a d, you get the next one. You add a d, d, d. So this d is this common difference, the common thing that you add to the previous one to get the next one. And if you do this, you see a0 will be there, and then you'll have a0 plus d, a0 plus d, another d has to be added, it's a0 plus 2d, a0 plus 3d, so on, so on, so on. So the nth term will have this wonderful looking formula, which is an equals a0 plus nd. Okay, so this is arithmetic progression. You might have studied it. It's a sequence. Once again, a very simple recursion defines it. Another very famous sequence which occurs all the time in practice, quite often you see them, is the geometric progression. Okay, what will happen often is you will say, I have some amount, there is an x% which gets x% of that something happens, and then another x% of that another happens. So basically you take an an and you multiply by r, you get the next value, and then you further multiply by r, you get the next value, and so on and so forth. So instead of adding a d, you are multiplying by an r. Okay, so this is very common in many cases. You may repeatedly multiply, like if you have some bacteria, they keep on reproducing, and they grow and grow and grow. There are lots of phenomenon which follow this geometric progression, and we saw that in some examples as well. So, if you have an A0, you will have an A0R next, A0R squared next, so on, and the nth term An is A0R power n. So, these are all very interesting sequences, and from a young age you must have studied many of these sequences in your school, and these have applications, far-reaching applications in many places. Okay, I am going to show you next a very interesting sequence which maybe you have not studied before, maybe you are not aware of this existence, but it's a very important sequence for us in this course at least. Okay, so these kind of sequences are very important. I'm going to call it the root 2 sequence. It's just my own name. I think it's quite popular and famous as well. You can look it up. It's called the root 2 sequence. By the way, what's root 2? And root 2, if you calculate in your calculator, it's this, it's an irrational number, as in the decimal points will neither repeat nor recur in any way, and they will not be finite also. They won't terminate, and no repetition also, right? So, it will keep on going 1.4, 1, 4, 2, 1, 3, 5, 6, 2, 3, 7, so on. Okay. So, this is square root of 2. Now, what is this root 2 sequence I am talking about? It starts with 2, A0 is 2, okay, and then I do this complicated looking recursion, but not that complicated. No? You can evaluate this. This is not very hard. An plus 1, the next value in the sequence, is the previous value divided by 2, an by 2, plus 1 by an. Okay, hope you got that. So, this is what I do to every an to get an plus 1. Notice this is slightly non-trivial. I am doing an by 2. If I stopped with that, it would be easy, but then I am adding a 1 by an. Okay, if I do just an by 2 without the second term, it becomes a geometric progression, right? So, it's just multiplication by half. But here that's not what I'm doing. I'm adding this 1 by an to make it very interesting. And let's just evaluate a few steps in this recursion just to get the sequence. It starts with 2, and then if I put an equals 2, what do I get? 2 by 2 is 1, 1 plus 1 by 2, 1.5, right? So, that's 3 by 2. And then if I put an as 3 by 2, I'm going to get 3 by 4 plus 2 by 3. 3 by 4 plus 2 by 3, you can evaluate it as 17 by 12. Okay, and look at that, that is 1.416666. If you put an equals 17 by 12 and evaluate it, you're going to get 577 by 408. And if you do the decimal expansion for this, it's 1.4142156686. Notice these guys. I hope you're seeing the connection between root 2 and this. Remember, root 2 is not a rational number, okay? So, you cannot write root 2 as some numerator by some denominator. It's not possible. You might have seen some proof of this earlier in your life, but you cannot write it. But notice how close this 577 by 408 has come to root 2. It's up to like some 6 decimal places, or maybe 5 decimal places. It's agreeing, or maybe even more, I don't know, 4 or 5 decimal places. It's agreeing with root 2 already, 577 by 408. If you put 577 by 408 here and evaluate the next term, you get this big looking 6 digit by 6 digit, okay. But notice what the decimal expansion is, 1.4142135562. Wow, it's coming so close, like 9 digits are the same as that of root 2, okay. After this, of course, this will eventually deviate a bit, and then it will start repeating also. I have not shown that if you keep on going, but then it appears that this little strange little looking recursive function I am doing seems to be giving me rational numbers which are coming closer and closer to root 2, okay. So, interesting, isn't it? So, look at how non-trivial a sequence can become, you have root 2. What is the property of root 2? If you square it, you get 2, right? It's a property. No rational number, no integer, if you square, you're going to get root 2, right? I mean, no rational number will square like that. But root 2 is a number which we imagine exists, and it has that property, and it's sort of decimal expansion. Well, you keep on going, you can't fully specify it, you have to keep on going. Now, it appears that you can have a sequence of rational numbers. See, these sequences are all rational numbers, no? Because, I'm starting with 2 and I'm putting something here, and I will always get a p by q, right? I will get a numerator and a denominator. and these fractions seem to be getting very close to root 2. Okay, some sort of magic is going on here, isn't it? So you can do root 2. So previously in my problem 1, I asked you, how do you evaluate root 2? How do you find the decimal point expansions for root 2? And this seems to be sort of a solution, right? Sequences seem to be interesting, but they also deviate. It's not like that's exactly root 2. So what's the connection between this sequence and root 2? Okay, it's a nice question to ask, and we will try and answer these questions later on in these lectures as we go along. So these are some examples. So you see, recursive definition of sequences has the potential for huge number of applications, and it's very important to understand them. Okay, so now how do you visualize sequences? Okay, so it's always good to visualize, right? So have a mental picture of what that sequence is, make a plot. So we saw always that Desmos gave us wonderful insights into a function. You take a function, you just plot it in Desmos in a graphical calculator, you see what it is. Okay, so likewise here you can visualize sequences using a plot method called stem plot. Okay, so this is I've actually used Python's module called matplotlib to plot this. You can take a Python notebook and do this. I know you may not know Python so well, but there are so many tools today that can give you plots like this. And like I mentioned, Python matplotlib is what I've used. You can use other tools as well. Okay, so it's exactly like a graph, but except that we're not joining and all, right? So because there is only, the function is defined only for integer values of n. So I can't join and draw a smooth curve. I have to only draw the value taken by this, and this is called a stem plot. So you notice here, if an is n, n equals 0, it's a stem of height 0. N equals 1, it is a stem of height 1. N equals 2, it is a stem of height 2, and so on. So you can see these are called stems. These are like little pins with needles that you plant there. Of the height determines the value of an. Okay, simple, isn't it? So an equals n has this very simple looking stem plot. It will also increase like this, and it will look like. Here is minus 1 power n. Notice what happens. For n equals 0, it is plus 1. N equals 1, it is minus 1. 2, it is plus 1. 3, it is minus 1. So notice how the stem sort of does this up and down and up and down. It's just a very easy way of visualizing what this function is. Here is my function 1 by n. I'm calling it 1 by n. I mean, it's okay, 1 by n plus 1, whatever, right? So it can also be 1 by n. I mean, you start at 1. If you start at 1, it will be 1 by n. If you start at 0, it's going to be 1 by n plus 1. It's just a starting shift. So it starts at 1, and then it goes to 0.5, 0.33, 0.25, 0.2, so on and so forth. Okay, and so you notice here how the stem plot sort of captures how this is falling in a graceful small way, and how that works. Here is a Fibonacci sequence, and Fibonacci sequence sort of seems to be growing up exponentially, So notice how, in fact, the next value will be even higher, right? Some of these two, it will go all the way there. It seems to be shooting up exponentially. In fact, if you know some theory, you'll know that the Fibonacci sequence is actually exponential. You can write it as the exponent of some famous number. Okay, so you can do all that. We'll come back to maybe see it later on. So Fibonacci sequence has this kind of visualization. Here is an AP, arithmetic progression, 2 plus 5n. So A0 is 2, D is 5. Okay, so you see here, this is sort of growing in one smooth linear way. Okay, this is linear growth, 2 plus 5n. And here are two geometric progressions, one with the common ratio r being greater than 1, and A0 is 3 into 2 power n, and you can see that the thing is exponentially blowing up. The other is a common ratio less than 1, 0.5 power n, and then 30. So if you do that, then you see that this an is exponentially falling down. It falls very rapidly down to 0, takes very small values very quickly. Okay, so this is the plot of an. So this just gives you a way of visualizing sequences instead of writing down dry expressions. If you like to see the sequence, you can do it with these stem plots. A lot of arguments that I will make to motivate the sequences in the study will be graphical. I will just use the graph to make some quick arguments. A little bit later on, we'll see analytical methods for how to argue these things. Okay, so that's the visualization. Okay, so let me close this topic with saying a little bit more on the root 2 sequence, right? Hopefully you're mystified by that root 2 sequence, how it came about. Let's plot the root 2 sequence. So you see here, A0 is 2, and then I got 1.5, and then I got like 1.4 already. And then slowly notice how it is flattening. No, it's just it seems to be all the same after this point. Okay, so this is a recursion. You got this here. So once again, root 2 is irrational, and we don't know how to compute it, how to keep computing decimal places. On the other hand, this an is rational, right? And it can be computed precisely. Any rational number, it's numerator by denominator. I can do long division. I can get any number of decimal places I want without any problem. And wonderfully well, this an is flattening to some particular value. It seems to be, going to one particular value, and it turns out we can show later on that that particular value is actually root 2. Okay, and this method, this kind of flattening and tending to one particular value is very, very useful, because I can now compute root 2 to any amount of accuracy. I'll just keep going for larger and larger and larger value of n till like sort of convergence, until I get the same number of decimal places, and these are just fractional evaluations. Okay, so this slide sort of tells you why the root 2 sequence is important from a computational point of view, function evaluation point of view. Okay, so hopefully this gives you justification for why sequences are useful. Okay, so let me just do one more little quick application. We won't say anything else about this. It turns out sequences have wonderful applications in electronic systems. Okay, so mostly when you deal with signals in electronic systems these days, you use discrete time sampled signals. Okay, and these are represented as sequences. Okay, so the digital signal processing that you will study later on represents signals as sequences. So here's a very, very famous sequence that appears again and again and again in all of electronic systems, and that's the input sequence. It's shown here. It's a sinusoidal sequence. It has this sinusoidal shape, sine wave as it's famously called. So far we haven't introduced the sine function in this course. We will introduce it later on. So here is an example of what's called a filter in digital signal processing and electronics and all that. So you have an input sequence xn, and this filter will put out an output sequence yn, and this yn is related to xn and the filter coefficients in this fashion. Okay, so this is a very common way of writing out a filter. And notice this big sinusoid has become one small sinusoid after this filter. You can design filters like this later on. Hopefully you will learn it in some of your later courses. So sequences are not just for idle theoretical study and function computation and all that. If you know about sequences and how they behave and know their properties, you can be a better electronics engineer. Okay, thank you.